What happens when a million users hit your application at the exact moment a data center catches fire? Right now, half this grid is offline. We are looking at a simultaneous dual failure. The first variable is an instant traffic spike. 1 million concurrent users requesting complex machine learning predictions at the exact same millisecond. The second variable hits right at the edge of that spike. A hard, unrecoverable power failure has just severed Availability Zone A. In a traditional on-premise data center, this specific combination of extreme load and lost physical capacity is fatal. The remaining physical servers would choke on the sudden overflow. Databases would encounter cascading locks as they scramble to handle dead connections, leading to a total hardware meltdown and complete application blackout. Modern cloud environments operate on the assumption that physical hardware will fail. These serverless distributed systems are designed to detect localized damage and initiate an autonomous, real-time adaptation of the underlying architecture. Let's freeze the system right at this moment of maximum stress to map exactly what we are working with. At the very edge of the topology, we have an Amazon Lex AI chatbot interface. This is the entry point receiving that immediate influx of user intent data. Looking at this topological map, you can see the standard serverless flow. The Lex entry point passes distinct data packets into a central compute cluster, powered by AWS Lambda, which then routes those executions down into an organized storage grid, Amazon DynamoDB. You can see the immediate physical threat right here. The central compute layer is taking the full brunt of the traffic spike before it can even execute the incoming requests. This leaves us with a critical architectural problem. How does a distributed system prevent a global downtime event when the underlying physical hardware powering it dies right in the middle of a transaction? To answer that, we have to look closely at how the Lambda compute nodes are reacting to this traffic influx. Lambda operates on the concept of stateless execution. Because the code doesn't rely on local underlying servers to store session data, it isn't bound by strict physical hardware constraints. Instead of buckling under the pressure, the single compute node begins cloning itself. It multiplies into hundreds and thousands of identical copies, spreading outward like a neural network to absorb the initial API shock. This reaction happens in mere milliseconds. Thousands of fresh, isolated execution environments spin up concurrently to meet the exact size of the load. If you tried to handle this with traditional servers, you'd spend vital minutes waiting for new virtual machines to boot up, provision, and register with load balancers, long after the system had already crashed. Stateless elasticity converts a catastrophic, unpredictable traffic spike into a highly distributed, manageable compute load. However, infinite compute scaling introduces a significant risk. If the compute layer scales too fast, it can unintentionally run a distributed denial of service attack on its own downstream resources. Specifically, the stateful database, DynamoDB, mechanically cannot ingest and write data as fast as the massively scaled Lambda functions can process the incoming requests. This flow diagram shows the component introduced to solve this exact bottleneck, Amazon Kinesis. It acts as an architectural shock absorber.
The central buffer queues massive incoming streaming data, releasing executions to the database at a slow, continuous, mathematically safe rate. This is known as backpressure management. It shields the stateful database from extreme traffic volatility by holding the excess load in a reliable queue. True resilience requires mechanically decoupling your data processing speed from your data ingestion limits. We've managed the data streams, but we still have to address the macro level of hardware blackout. Availability Zone A is entirely dead. At the network layer, the system continuously monitors the physical infrastructure using automated health checks, constantly pinging endpoints to verify they can still receive traffic. The moment those health checks fail, Amazon Route 53 steps in, acting as an autonomous digital switchboard to manage the global flow of requests. Through a DNS routing shift, Route 53 instantly cuts off the pathway to the dead zone and illuminates a new fiber optic route, redirecting all incoming traffic to a healthy secondary grid. This failover happens transparently. The end user never sees an error screen or experiences a dropped network packet. Hardware failure is a statistical certainty. Autonomous network rerouting provides the only viable strategy to maintain uptime when a data center goes offloading. With traffic successfully rerouted, we shift our focus from the external network down to the deep storage layer operating in the surviving availability zone B. This presents a severe logistical problem. How do you ensure data consistency when half of the physical storage grid holding your information was abruptly destroyed? This diagram illustrates DynamoDB's multi-region active-passive replication protocol. Whenever a data point is written in grid A, an identical mirrored point is pushed to grid B. When localized hardware dies, the secondary grid is already populated, ensuring zero data loss. We are looking at two very different mechanisms of survival. The compute layer survives through elasticity and rapid expansion, while the storage layer survives through strict redundancy and mirroring. True fault tolerance at the storage layer demands geographically distributed syncing long before a failure event ever occurs. Pulling back to a macro view, we can see the entire architectural structure. It is fully restored, expanded, and handling the heavy load. The compute layer absorbed a localized shock by leveraging stateless elasticity, while stream buffering protected the database from the resulting surge. Simultaneously, the infrastructure bypassed a catastrophic hardware failure through automated DNS routing and continuous multi-region data replication. The most critical aspect of this entire lifecycle is the total absence of human intervention. No engineer received a pager alert. No one had to manually provision a backup server or run a database restoration script. Legacy strategies that focus on static infrastructure provisioning are ineffective in modern environments where traffic and hardware health are in constant flux. The integration between APIs, compute nodes, and replicated storage mirrors the way organic systems isolate damaged cells and redirect resources to healthy ones. Cloud architecture has evolved into the engineering of autonomous ecosystems, environments where chaos is treated as a baseline condition to be mitigated in real time.